Hello everybody. Sorry I won't be there today because we have the meeting with the minister. A quick note, once again, this is just a reminder of where our office hours are. We have a TA tutorial tomorrow on Tuesday, just ahead of the midterm, which is on the evening on February 10th. And again, your names will be up on Canvas, split by last name. So last time we got into this discussion of functional group derivatives, and we described three kind of general classes of reactions, right? We have our strongly basic system, so that's where something like hydroxide is attacking something with a reasonable leaving group. Our strongly acidic mechanism, so this is something where we would use something that's not a very good leaving group, we're activating it, something similar to like an SN1 reaction. And then the mildly basic, this is kind of in the middle where we have not too bad of a nucleophile, not great of a leaving group, it's sort of in the balance. And really, again, these are three general classes of reactions to remind you about the kinds of transformations that are possible and also kind of bucket together the mechanisms that we've seen before. Now, today, we're going to talk about specifically substitutions involving esters. So esters are going to be our major focus for the starting materials or the products here. So really walking around that kind of middle tier. These break down into what we call Fischer esterifications. We've mentioned these before. We're going to look at the mechanism today. We're going to talk about saponifications. So this is where we are breaking down the reaction. And again, you've probably heard of this term before. It's saponification is like a soap formation. Transesterification, this is where we're switching the OR group between two different centers. And then finally, conversion of esters into amides. So this is walking down that energetic pathway we've talked about before to our most stable amide structure. So first is just a general sort of level setting. We're talking about our esters as these molecules, and remember we've got some reactions we talked about their formation, and today we're going to talk about more what we do with the esters once we form them. So just as a quick guidance, remember we talked briefly earlier about the alkylation and diazomethane reactions. That's where we're adding this R group and we're keeping the rest of this chunk in place. So this carbon-oxygen bond stays intact. We're just adding this R to that carboxylate. On the other side, we have our Fischer esterification, lactonization. That's where we're adding this entire package, the oxygen and R. We're breaking or forming this bond here, and that's mainly what we're going to be talking through in that case because those involve more nucleophilic substitution at the carbonyls like we've been discussing. On the other side, once we form these, we can hydrolyze them under acidic conditions. We can what we call saponify them or break them down under basic conditions. So this is how we transform away from those. Transesterifications are sort of reformatting this where we're changing one OR for a different OR group. That's why it's called transesterification. And then finally, esters to amides, where what we're doing is we're substituting this group for our NR part into a more stable amide product. So as a review, remember these are all two-step transformations, or at least any ones in kind of this middle ground right here. These are two-step transformations where what we're doing is both that first nucleophilic addition to form a tetrahedral intermediate. That tetrahedral intermediate is going to go some kind of substitution where the nucleophile stays in, and we've now ejected our leaving group. So the leaving group has departed, and we've now kicked it out of our overall transformation. And remember, what we're talking about here, really, which mechanism we go through depends on how good of a nucleophile we have and how good of a leaving group we have. That sort of breaks down to those three generic categories we talked about before. So the first one we're going to discuss as far as ester making is this Fischer esterification. Now we briefly mentioned this part before. It involves a carboxylic acid along with an alcohol, and we're using catalytic acid to form these products where again what we're forming here is this OR bond. In the end, this ROH is made up of that piece right here. This is the bond that we're actually breaking and forming, and we're ejecting water. So this OR group here, let me just change the color. That OH is being ejected as our water fragment. So this is just sort of tracking where the oxygen is going here to conceptually show you the bond making and breaking systems. This is one of the most common ways of making esters and something that we've probably done in labs at different points too. So if you look at the general mechanisms we discussed before, we had our strongly basic, strongly acidic, and then the sort of mildly basic. This follows under the strongly acidic kind of mechanisms. Typically, what we're doing here is we're doing an addition to our carboxylic acid using a strongly acidic sort of media. If you notice the fragments we discussed, our leaving group here is OH, not a good leaving group, so we're going to have to activate it. And the nucleophile we're going to be using is probably this neutral, after we've transferred the proton, it's a neutral alcohol. So we don't have a great nucleophile. We do not have a great leaving group. That's why we're under these strongly acidic type conditions here. That's the mechanism that we're going to be following in. So because of that, first thing we're going to do is a transformation where we're going to be activating our carboxylic acid. So our R group is going to activate our carbonyl. We now have made the carbonyl electrophilic enough. Also, as a result of that, we have transferred off or made our alcohol neutral in this case. Now, remember, for most of these Fischer esterifications, the alcohol doubles as our solvent. So now that we've made this fragment, this is our nucleophile. It's nucleophilic enough to do our addition. And that's going to give us our tetrahedral intermediate. Now, because we're under acidic conditions, we are also going to have our positively charged intermediates in this case, like this. All right, so that's our first step. Now what we have to do is some type of proton transfer. The goal of this overall transformation is we're substituting and actually losing water from the system. So after we've got this intermediate, we're going to have another molecule, let's say, of solvent floating around. We're going to use this green one. Let's say we have another molecule of our alcohol. Its job is to pick off the proton. And again, moving forward in the mechanism, we're going to deprotonate at this center over here. That's going to give us our now neutral tetrahedral intermediate, where we've now brought in this OR fragment here. So we're moving forward. Remember, to get to our final product, the major thing we have to do here is we're going to reform this carboxylic acid, or this carbonyl center here, to give us our ester, which means we have to get rid of this OH as water. We still have an extra proton over here. We're going to have to protonate the center to help it lose that group. And now that we've transferred the proton back to our solvent, we've also got one molecule of our protonated solvent, like this, which acts as our charge carrier. So we're going to move forward, and I'm going to protonate that center. What I'm doing is I'm getting that leaving group ready to leave. I'm aiding in that leaving group like an SN1. I'm making it into a better leaving group. So now we've got our OH2 plus and OR. Now that we're set up like this, we're in a good spot to now reform our carbonyl. So we're bringing down the charge again into our carbon-oxygen sort of center. So we get a carbon-oxygen double bond, and we are kicking out this group over here to lose our water. So now we're going to have almost finished. We've got our carbonyl back in place. Positive charge is now on the center. We've swapped out that carboxylic acid. We now have our OR group in there, and we've lost one molecule of water in the process, which means last step here is to basically pick up with our solvent or our water this extra charge, and then give us back our final molecule, like that. So this follows the same pattern that we've used for our strong acid nucleophilic acyl substitution. Major points here is we have to activate the carbonyl first to make it more electrophilic. We bring in a neutral nucleophile, making charged intermediates. We're picking off that proton and making the leaving group into a better leaving group by protonating it. We then recollapse, getting back our proton. This is our catalytic acid that we are transferring back, which is what we use restart this next cycle. So this is the Fischer, or sorry, the Chem draw version of the same point, just drawn out. Now we're just emphasizing things like chirality as we go through this, and again tracking where those oxygens go. So just here again to point it to it. Color coding patterns, this oxygen is the one we're departing. We're bringing in a new oxygen from the alcohol. We're losing that first oxygen as water, and we're forming a new carbon-oxygen bond with the incoming alcohol. So applying it, this is similar to something we've described before. What are the reagents we're going to need? Remember, if this is Fischer esterification, we're breaking about that bond there. So the two pieces you're going to need is a carboxylic acid and the corresponding alcohol. And if we're going to write the acid catalyzed mechanism to produce it, let's draw that one out. This is just a longhand version. I recommend that you guys pause the video, give it a chance where you want to write out this mechanism using the acetic acid, that sort of 2-carbon fragment, and remember at some point we're going to have to bring in this long chain alcohol here as our alcohol component, where that would potentially again be the solvent in this case. And it's going to be under acid catalyzed conditions, so we can start off by saying, sure, we've got a proton because we used phosphoric acid or something like that, and we have protonated alcohol as our carrier. So pause it for a second, give it a shot, try to draw this out. Now, when we're doing the acid catalysis, first thing we're going to do is transfer the charge. That's going to give us this protonated carbonyl. Then we're going to bring in our neutral nucleophile into that center. That's going to give us our tetrahedral intermediate, OH, H, and OH, like this. All right, now that you've got these fragments, we're going to take this and we have to use another molecule of solvent. Let's use second molecule here. I'm just going to draw as our charge carrier. That's going to pick off this proton and give us back our neutral tetrahedral intermediate. H, O, blah, like that. Now we're going to have to use this guy. This is our HOH positive, yada, 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 like that. And we are going to protonate, let's say. And again, in this case, I'm choosing the oxygen on the left. Sorry, just trying to redraw that a little cleaner. Oxygen. And we're going to redraw it like that. So that's going to give me a OH2 plus over here, OH, and our fragment. And now bring the lone pair down, eject that group like this. That's going to give me my penultimate product. It's now positively charged over here, and we have our fragment all attached. And the final step, I'm just going to say, is some other alcohol fragment is going to pick off that to give us our charge and our final product over here. That's regenerating the catalytic acid that we need to get this process working. So the next thing to discuss is lactonization. So lactones, or the process of making lactones, is making cyclic esters. It's really the exact same process we've discussed before. Again, the only thing that is different is now we're making these 5 or 6 membered rings, meaning that it is still the coupling of a carboxylic acid with a alcohol. It's just both of those two fragments, the nucleophile and electrophile, are attached to the same carbon chain where you can make these 5 or 6 membered rings. The formation of these esters really follows the same mechanism we've discussed for Fischer esterification, and likewise the hydrolysis follows the same point. So really think of them exactly like esters. They can be hydrolyzed or transesterified under the normal things just like regular esters. Their only special feature is they happen to be cyclic, which means that both the electrophile and nucleophile are present in the same molecule. So just to practice this out, let's say we had these molecules shown here. If we're trying to make their lactones, what we're saying is, in this case, the carboxylic acid center here, that's our electrophilic center, and the oxygen is our nucleophilic center, so that would count as 1, 2, 3, 4, and 5. So it's a 5-membered ring I'm forming. I'm going to just draw that out like this. And let's number it off. So based on what I had before, this would be 1, 2, 3, 4, and 5. Where carbon 4 has this alkene attached, so it should look like that. Sorry, that's oxygen number 1. So the cyclic molecule, we're just wrapping the two centers together. We're going to be losing this OH as water, and all of the species stay in place. So the alkene is still attached to carbon number 4. In the one at the bottom, once again, our nucleophile, we'll call that carbon 1, 2, 3, 4, 5, and 6. This is now a 6-membered ring, and I'm just going to draw it sort of like this, where this is the oxygen, carbonyl, and I'm going to draw it as 1, 2, 3, 4, 5, and 6. Like that. So one thing to notice, carbon 3 has this methyl group attached to it. I've drawn it purposely so that the geometry here remains the same as what I've got as the geometry over here. So I'm basically keeping them common so that the wedge that I have over there is the same. Remember to double check this. You can look at this side. This would be priority 1. So let me change the color of that. If we did our CIP rules, priority 1 would be this group, priority 2 is this group, 3 is the methyl, and the proton to the back is priority number 4. That is a S center, and likewise we have priority 1, 2, 3 is the methyl, and hydrogen is number 4. This is still an S center here. So you can always go back and do your CIP RS notation to double check your work. Now, all these Fischer esterifications that we talked about are equilibria. So that means that the mechanism that we use to form them under acid catalyzed conditions really is exactly the same to break them down. This is similar to what we saw with acetal formations. Acid catalyzed formation of acetals happen with the extrusion or loss of water. And if we use water and acid, we can walk the same mechanism backwards to return us to where we started off. So the Fischer esterification is the formation of the ester under acid catalyzed conditions. We can use the same mechanism for hydrolysis. The only difference with hydrolysis is the nucleophile is now water, where if it's under esterification, the nucleophile is equal to ROH. So the similarity you can see is there's still these neutral OH type nucleophiles. We're just changing off. One of them is water, both are, and the other one is our alcohol. But same mechanism. So in that same way, if you're used to looking at an alcohol and a carboxylic acid where we condense them together to form our ester or lactone, we can do the reciprocal. So under acid catalyzed condition, if we're going to hydrolyze these, first thing we do is we identify the ester. We're saying we're going to be bringing in water to that center, and we're going to be clipping this bond here to bring in that OH kind of nucleophile. So the overall molecule here will be the same piece, so I'm just going to draw it in a similar geometry like this, and just numbering this off. Let's say this is center here is carbon 1, 2, 3, 4, and oxygen is 5. That would correspond to the center here being carbon 1, 2, 3, 4, oxygen is 5. So on carbon 3, we have our methyl group, and again I've tried to draw it so that I'm not having to do a bond rotation or something, so it's going to have the same relative orientation we see here. The last thing I need is this new bond. That is our OH that came from our water. So this would be the molecule. If I wanted to try and draw it out straight, so I'm just going to do, let's say, a rotation about this bond to kind of draw it more linear. I could draw this as the carboxylic acid like this. And again, let's number that off. So 1, 2, 3, 4. So that is 1, 2, 3, 4, and 5. Where in this case, carbon 3 will actually be presentation like this. It's going to be a wedge after I've done that rotation into that geometry. Okay, the next one, once again, we're clipping this bond over here. We're bringing in water as our nucleophile. This could be counted off as that center there is our carbon 1, 2, 3, 4, 5, and oxygen is 6. So keep the geometry similar just so that we've got similar presentation. Double bond over here, OH over there. We have a new OH tucked into here. And it's again our two centers haven't changed rotation like that. Where it's again 1, 2, 3, 4, 5, and 6. Okay. And if I was going to try and sort of straighten it out a little bit more, again, this one I'm just going to double check because it's a lot easier if I use my RS notation. So this would be priority 1, this is priority 2, 3, and to the back is 4. That's our hydrogen. That's number 4. So that looks like it's an S center. And I'm just going to redraw that in this orientation here. So OH, 1, 2, 4, 5, 6. So that's 1, 2, 3, 4, 5, and this is my 6. That's my OH. Okay, so I've got all of my centers numbered off. Now, as I'm drawing it like this, what I've done is I'm basically stretching this ring out in that direction. That means on carbon 2, right here, this should now be a dash, I think, and we're going to check that just in a second. And over here, this is oxygen is 1, carbon chain is 2, this is number 3, and hydrogen to the back is number 4, so this is an R center. So over here, oxygen is number 1. Let's say I drew methyl up like that. So 1, 2, 3, hydrogen to the back is number 4. That is still my R center, so that should be correct, I think. Let me just double check that. So 1, 2, 3, it's an R center looks good. All right, so that's how I would draw that center over here, is that presentation. The other one should be an S, so let's double check that. That's priority 1, 2, and 3. So as it's drawn, it looks like it's an R center, but remember the hydrogen, number 4, is actually facing us. So that means this is actually an S center as it's drawn right here with that methyl to the back. So that looks good. We are should be correct now that we've straightened out this molecule. So the next thing I want to briefly discuss is the concept of saponification. So what we're doing here is the term saponification comes from the process of making soap. To make soap is this, you may have heard it in that capacity. And what we're doing there is we're taking long chain fatty acids as salts. They are hydrolyzed by taking fats and oils and treating them with very, very, very strong base in order to make these carboxylic acids. So really what we're doing is we're taking these fats, which are really esters of these long carboxylic acids that have been condensed together, and we're cutting those ester bonds to free up the alcohol and the carboxylic acid. So this is our base catalyzed process. This is done under strong base. Even though we say it's base catalyzed, our nucleophile in this case is our hydroxide. So this is where we're using a very strong basic condition. If you look at this based on our mechanisms, because we're using a very good nucleophile here, this kind of falls into the same pattern as that sort of category 1. This is our strongly basic nucleophilic acyl substitution. We have got a good nucleophile. This is an okay leaving group, especially in the respect to this center here. And one of the things you can look at is this arrow. This is a process that's actually very, very equilibrium favoring the product. And if you look at this, this is partly driven based on the pKa's of the system. If I'm going in with a whole bunch of this hydroxide here, that center, that purple center, shows that oxygen is being incorporated right here. We're doing a nucleophilic addition and ejecting this group to form our alcohol. But if you notice, this strong base here, if we have a carboxylic acid, the original product that we're going to make will actually be the OH product. In the presence of the strong base, or even the strong of the alkoxide base, there's going to be an acid-base reaction here that allows us to form this much more stabilized carboxylate. So in this reaction, the strong base here is our good nucleophile plus the strong equilibrium push to form this very stabilized O- is probably what's making this reaction really much more favorable in this case. And this is why it's possible in such a favorable reaction. So the mechanism looks a lot like our strong base condition. The only difference here is that we are using actually 3 steps, not 2, if you remember counting back. So we're going to have our nucleophilic addition as we've planned. That's going to make our tetrahedral intermediate, just like in our previous case. Let's actually use our red color. So O- over here, we have our OR prime there, and we have our nucleophile, which is this OH from a hydroxide nucleophile. Again, why is this possible? Well, we're swapping one O- for another O-. It's at least energetically balanced like this. So once we've done this, next step moving forward in the process is the nucleophilic collapse. We're going to bring down this one and kick out this OR. Now, we've said this before, well, why don't I kick this group out? Totally possible. We would just be going back to our starting material in that case. So we're showing the productive mechanism where we're going to be ejecting this OR group as our process. So what that's going to give us is now our carbonyl being reformed. We are now making OR alkoxide, and we've now swapped in this nucleophile. So as I mentioned before in the last slide, this is not where we're going to stop. In fact, we specifically focus on this because we've got this very strong base in the case and a very strong acid. So we have this possibility of one final really, really positive, really favorable acid-base reaction, which is going to be very, very product favored to give us our carboxylate as our final material. So it's that final step here, that final sort of acid-base grab that allows this mechanism to be really, really product favored. So that's why we really emphasize in this case is an overall 3-step process. So that's just shown out here. We are following the same sort of nucleophilic acyl substitution under strongly basic condition. It's just a direct attack of a good nucleophile. We don't need to activate our carbonyl first. We make a negatively charged tetrahedral intermediate that then collapses, ejecting another negatively charged species. We then just have this follow-on reaction of this acid base, which gives us our final product. So now that we've talked about the saponification or conversions of either forming from ester or from acids and alcohols or breaking them down, esters breaking down to acids and alcohols, what we're going to do is sort of a swapping. And this is a case where what we want to do is start off with an ester where we have one OR bond. We're going to come in with another nucleophile where it's another alcohol, and we're replacing that alcohol group, swapping the alcohol out. And this can happen under either acidic conditions, so this would follow the kind of Fischer esterification type process, or we're going to do it under basic conditions where we're using our strong nucleophile here. So this one looks a lot like our saponification reaction. This one's going to look a lot like our Fischer esterification reaction. Remember, the main analogy here is we just showed you procedures where this group here could be OH, or the nucleophile can also be HOH. What I'm trying to emphasize is the addition or subtraction of water that we're doing in the reactions previous really are the same general mechanistic class and very same reaction where we just swap out to an alcohol where one of these groups from the water happens to be a carbon. You'll show that as we repeat these in the next couple slides. So first, under strongly acidic conditions, the transesterification really follows the generic strongly acidic mechanism. It's really just the Fischer esterification mechanism where instead of having a alcohol here or the carboxylic acid here, we're starting with this ester. So just if you trace this part out, we start with an ester in place where we have one particular R group. We have a strong acid. We're going to activate the carbonyl just like we've done previously. Nucleophilic addition of our neutral nucleophile to make a positively charged tetrahedral intermediate. That's going to then undergo a proton transfer step to give our neutral tetrahedral intermediate. We then activate the leaving group by a proton transfer, so we still want to get rid of this alcohol fragment. Collapse the tetrahedral intermediate to make our positively charged material. And if you notice, overall, what we're doing is this alcohol here is being swapped in to that fragment, and we are ejecting. This alcohol fragment is now departing in this step down here. We end up with another product. And the final acid-base reaction gives us another ester. So we're reformatting that alcohol fragment. This is, again, really the same mechanism as a Fischer esterification. It just happens that we don't have a carboxylic acid in this position. It's an ester instead. This also emphasizes why you have to be careful of your choice of your solvent. If you had an ester under strongly acidic conditions where ethanol or propanol, let's say, was your solvent, because there's more of it, will tend to overcompete and actually swap in and replace whatever ester you have with the alcohol from the solvent itself. So you have to be careful if you don't want your solvent to be impacted in the reaction. It has to match the alkyl fragment that you're actually dealing with. Under strongly basing condition, it's really the classic two-step attack, nucleophilic attack and collapse. We go in with our strongly basic alcohol. In this case, it's going to be deprotonated to make our alkoxide. That nucleophilic attack makes our anionic tetrahedral intermediate that when it collapses, we're just ejecting this other alkoxide here. So in both of these reactions, what you're seeing is we have really an isothermal sort of case. The overall energy balance here does not favor one side or the other, because here we're starting with an alkoxide and we're making an alkoxide. They're really about the same stability, so the way we do this is Le Chatelier, right? Lots more of this one, or some way to potentially remove this, would allow us to drive it to products. In the previous example, it's really the same thing. If I go in with a whole bunch of this material, I'm going to push it towards this product, so it's really done by mass balance in Le Chatelier. So let's look at these ones here. If we're going to carry out these transesterifications under strongly acidic or strongly basic conditions, look at the conditions here that are applied and see which ones we're using. In the first example, we are going in with an alkoxide. That is our strongly basic condition, and we're going to be doing a substitution where this alcohol is going to sub out this alcohol group here. Now, if you notice, there's actually 3 of those in this molecule. So what we have here is an alcohol, 3 groups attaching, and we have a new alcohol that's going to substitute at each of these kind of ester centers. That's why we have also 3 methoxides designated. So what I'm going to get is 3 molecules of this new methyl ester, and we're going to also eject the alcohol portion as this triol, like that. In the second case, if we're taking a neutral molecule and a neutral ester, these would be the strongly acidic conditions here. This is where we're going to have to go in with something like HCl or a strong acid in order to help to catalyze this process. Very similar sort of overall transformation. We're going to be breaking this bond right here. We're ejecting this that alcohol fragment, and we're installing this new alcohol fragment into here. This is opening a lactone when we do this case because we have a cyclic ester here. So I'm going to draw this out as the alcohol fragment And again, just to number this off, let's call this 1, 2, 3, 4, and 5 is 1, 2, 3, 4, and carbon number 5, where the new incoming alcohol is this ethyl group, like that. So this is what it look like directly. You could also redraw this in a more linear form, not sort of curved back on itself, but we're clipping that bond effectively to bring in this new alcohol. So our last transformation is taking esters, and we're using a nitrogen nucleophile. In this case, we're doing our amides. So if you had to do these conditions, think about this for a second. How might you apply this if we use strongly acidic, strongly basic, or mildly basic? And while you think about this, I would ask you to pause the video for a second, come up with an answer that seems to make sense for you. And the best way to do that is look at each of the conditions and try to rationalize, is there something that might be incompatible about these conditions with the reagents you've been given? So let's take these one by one. Under strongly acidic conditions, we're going to have a whole bunch of protons. Now protons, right, strong acids like this, remember we actually have a pretty good base in this system in the amine. So if we go in with strongly acidic conditions, we're just going to do acid-base chemistry, which means this is no longer a nucleophile, so that's not going to work out. We can't use strongly acidic conditions to do this kind of insertion. Because the nitrogen is going to just compete and grab that proton. So that's out. All right, strongly basic conditions. Now that would be something kind of like using hydroxide or something like this, right? That would be normally what we do. That's not great either, because remember, hydroxide plus our carbonyl, those are just going to give our saponification reactions, which once we've got these, acid-base, right? This is also not going to work out. So that's not super awesome. What we're left with is kind of the only choice we can still do is these mildly basic conditions. Now this is one of the things where reactions like this, turning esters into amines, we can do it energetically. It is favorable to make this amide bond. Remember we described this where this delocalization is, and the resonance structures that are possible there are quite favorable just because of where the electronegative atoms that we have. But just in general, this is not a super fast reaction. It's kind of grudging. You're going to see this as we do the mechanism where we are forming some relatively unstable or kind of higher energy intermediates. So while this is absolutely possible, it generally requires more temperature, more forcing conditions to really get the reaction done. But energetically, it is possible because we're going to this more stable structure from our ester. So let's look at this under sort of mildly basic conditions. So this is where we're going to be pushing this through, kind of like our imine formations again too. We're going to start off with a nucleophilic nitrogen without activation, and we're going to start with our carbonyl with no activation. So we're just doing a simple nucleophilic approach to give us our first addition. So when we do that, we end up our negative charge over here. We end up with our O, our prime, and we end up with our nitrogen H, like so. So this is again similar to what we saw with our imine formation. We now have a zwitterionic molecule where we have extra protons in our nitrogen and negative charge on that center. So while we're under mildly basic conditions, remember we've got an excess of amine floating around. So that's going to act as our proton carrier in the system. We can pick up that proton. And again, I'm just leading off with that as our first step just because we have our amine present. So we're going to deprotonate first. Now when we do that, we're going to end up with our anionic tetrahedral intermediate. Like this, and our charge carrier sitting on our amine. Now, we can do a couple different steps from here. You can imagine a case where we're going to balance out the charge between these two, and that absolutely can be possible, but I'm actually going to stop right here and continue to move forward with this one. The reason why is, remember, in order to get this reaction to go forward, we have to bring the charge down. In the end, we want to reform this carbon-oxygen double bond, and we have to kick out one of these groups, right? We just installed this nitrogen, so bringing this down and booting this out like that, not super favorable because we'd be losing a nitrogen minus, right? If we were really wanted to kill up this off, we'd have to transfer that proton back to get to something more like this. This is now much more likely to be a decent leaving group, but like we said, under the kind of mildly basic conditions, proton transfer is going to be fast. We're going to be stuck right here. And I want to keep this negative charge because, look, if I bring this down directly, I'm booting out an O minus. So this becomes at least something that from this intermediate, I've at least got something that's energetic parity, right? I am going to bring down this O negative and kick out an O negative to give me my amide and my alkoxide leaving group under that condition. And again, what I'm really emphasizing here is, well, at least we had an alkoxide, we formed a new alkoxide, that's at least energetically balanced, so that's not too bad. Where this thing can help us to go forward is, remember, we've still got this charged amine here. So the proton carrier, the extra base, is going to hold on to this, and what we're going to do is bring back this acid-base reaction. That final acid-base reaction is going to help us to quench out that extra charge that we've got and give us back our neutral amine to continue the reaction. So this is nucleophilic enough to participate back in the next cycle over here, where final proton carrier is this system here. So this is just that whole process drawn out in good copy. Once again, just highlighting those steps. Neutral nucleophile attaching the neutral electrophile, very much like we did with our imine formation. We've got a zwitteronic intermediate that we're picking up a proton on, so that's just transferring it back to make our negatively charged one. Once again, we just leave with this one, bringing down that negative charge to help boot out our O minus. We're just saying that, okay, I have an alkoxide, I'm making an alkoxide, that's at least energetically equivalent. If we do that, that alkoxide now can carry out this acid-base reaction. Remember, this has the alcohol has a pK of in the 15s. This has a pK in at about 10. So this is quite favorable to go to the acid-base reaction you see over here.